Hello, and welcome to Some Neuromind. I'm glad you're here tonight. Maybe the day left something behind that you're still carrying, a thought that keeps returning, a tension that hasn't quite released. Or perhaps you're simply the kind of person who finds it easier to let go of the world when there's something vast and quiet to drift toward. A place so far removed from the ordinary that the ordinary loses its grip. Either way, you've come to the right place, and there is nothing required of you now except to breathe, to settle, and to follow. Tonight, we are going down, not into space, not into history, but into the ocean, all the way down, past the sunlit layers and the dimming blue twilight, through the darkness where pressure builds and temperature drops, and the familiar rules of the surface world no longer apply. We are going to the ocean floor, a landscape that covers more than 60% of the Earth's surface and that most humans will never see. A place of mountains taller than Everest, plains wider than continents, and trenches so deep that the entire atmosphere would fit inside them with room to spare. It is a world that existed long before life moved onto land. It is still changing, slowly and enormously, tonight, while you sleep. Before we begin, if Some Neuromind gives your mind a quiet place to rest at the end of the day, please consider subscribing. You're already the kind of person this channel was made for, one quiet mind at a time. There is much to discover tonight. Before we are done, we will encounter something living in a place where nothing should be able to live, and something ancient embedded in the seafloor that carries the memory of a world millions of years before our own. But there's no hurry. We'll go slowly and gently, one quiet fact at a time. Let's begin. The ocean floor is not a flat and featureless plain. This is the first thing to understand, and perhaps the most important. For most of human history, the deep seafloor was imagined as a vast, uniform mud, a dark and empty expanse with little to distinguish one region from another. What detailed surveys have revealed over the past century is something far more dramatic. The ocean bottom is a landscape of extraordinary variety, soaring mountain ranges, deep fractures, broad volcanic plateaus, towering isolated peaks, plains buried under kilometers of accumulated sediment, and trenches of such extraordinary depth that they remain among the least explored places on Earth. If you could drain the oceans entirely, you would be looking at a terrain more varied and in some places more extreme than anything visible on land. The mid-ocean ridge is the longest mountain range on Earth, and almost no one has seen it. Running for approximately 65,000 kilometers around the globe, more than 1.5 times the circumference of the Earth, the mid-ocean ridge is a continuous chain of underwater mountains formed where tectonic plates pull apart and molten rock rises from below to fill the gap. It winds through every ocean basin, cutting across the Atlantic, curving through the Indian Ocean, threading across the Pacific. Where it comes closest to the surface, it breaks through to form islands. Iceland sits directly on it, as do the Azores and the volcanic Galapagos. The ridge is not a single gentle hill. In places it rises several kilometers from the surrounding seafloor. At its crest, volcanic eruptions build new ocean floor continuously, the Earth adding to itself in slow and steady increments, one lava flow at a time. New ocean floor is being created right now, where the tectonic plates diverge along the mid-ocean ridge. Molten rock, magma, rises from the mantle beneath, squeezes through the gap between the separating plates, and cools almost instantly on contact with the freezing seawater. This process, called seafloor spreading, generates new basaltic crust at a rate of a few centimeters per year, roughly the speed at which your fingernails grow. Slow by any human measure, but over millions of years it is enough to entirely replace the ocean floor. The oldest ocean crust in existence is roughly 340 million years old. Continental crust, by contrast, can be 4 billion years old. The seafloor is continuously being made and remade, recycling itself through processes that operate far beneath our awareness. The deepest point on Earth reaches nearly 11 kilometers below the sea surface. The Challenger Deep, located in the Mariana Trench in the western Pacific Ocean, descends to approximately 10,935 meters, just under 11 kilometers. To place this in perspective, if you took Mount Everest, the tallest mountain on land, at 8,849 meters, and submerged it entirely in the Challenger Deep, its summit would still be more than 2 kilometers beneath the surface. The pressure at that depth is approximately 1,100 times the pressure at sea level. A human being transported to the bottom without protection would be crushed almost instantaneously. Yet life exists there. Organisms have been found in the deepest trenches that have adapted over millions of years to these crushing pressures, evolving bodies and biochemistries with no parallel anywhere on the surface of the Earth. The ocean covers about 71% of Earth's surface, but we have mapped less than 25% of the seafloor in detail. This statistic is not a reflection of lack of interest. It is a measure of how extraordinarily difficult deep-sea exploration is. Satellites can map the surface of Mars with higher resolution than we have mapped much of Earth's ocean floor. The primary tool for seafloor mapping is multi-beam sonar, which sends pulses of sound downward from a research vessel and measures the time it takes for the echoes to return. Each pass of a ship maps only a narrow strip of the seafloor below. To cover the entire ocean at the resolution needed to see features smaller than a kilometer across would require an enormous fleet of research vessels operating continuously for decades. What we have is a patchwork of detailed surveys, with vast regions known only in broad outline. Hydrothermal vents are among the most extraordinary environments on Earth. In 1977, scientists exploring the Galapagos Rift, a segment of the mid-ocean ridge in the Pacific, found something that changed biology permanently. At depths of around 2,500 meters, far below the reach of sunlight, they discovered chimneys of mineral-rich water erupting from the seafloor at temperatures exceeding 350 degrees Celsius. Around these chimneys was life, dense, thriving, improbable life. Tube worms meters in length, ghostly white crabs, dense clusters of mussels and clams, shrimp gathering in crowds around the vent's edges. None of these organisms depended on sunlight. They were powered instead by chemical energy, specifically by the hydrogen sulfide and other compounds pouring from the vents, which bacteria at the base of the food web converted into organic matter through a process called chemosynthesis. It was the first ecosystem ever found that ran entirely without solar energy, and it transformed our understanding of where life can exist, and perhaps where it originated. Black smokers build chimneys of mineral on the seafloor. The most dramatic hydrothermal vent structures are black smokers, columns of superheated water so loaded with dissolved minerals that they appear as dark plumes rising from the seafloor. When the hot, mineral-rich fluid contacts the freezing seawater, the dissolved metals precipitate out almost instantly, falling as fine dark particles that settle around the vent opening and gradually build a chimney of sulfide minerals, primarily iron, copper, zinc, and lead. These chimneys can grow to heights of 20 meters or more. They are not permanent. They can collapse, become blocked, or be destroyed by volcanic activity, only to be replaced by new structures forming nearby. Each black smoker is a temporary monument, built and dismantled by the same geological forces, housing a community of organisms that must move when the vent goes cold and find a new one before they starve. Chemosynthesis supports entire ecosystems in the absence of sunlight. At hydrothermal vents, cold seeps, and other deep-sea environments where chemical-rich fluids emerge from the seafloor, life does not depend on photosynthesis. Instead, it depends on chemosynthesis, the process by which certain bacteria use the chemical energy in compounds like hydrogen sulfide, methane, and ammonia to produce organic matter. These bacteria form the foundation of an entire food web. Above them feed tube worms, clams, mussels, shrimp, and a variety of other organisms, some found nowhere else on Earth. The tube worms found at hydrothermal vents have no mouth, no stomach, and no digestive tract. They contain dense colonies of chemosynthetic bacteria within a specialized organ called a trophosome, which occupies much of their body cavity. The bacteria provide all the organic carbon the worm needs, and the worm provides the bacteria with hydrogen sulfide and oxygen drawn from the surrounding water. It is one of the most intimate symbioses in the animal kingdom. Cold seeps are where methane and other gases leak slowly from the seafloor. Not all chemosynthetic ecosystems are associated with volcanic activity. In many areas of the deep ocean, particularly along continental margins, natural gas, mostly methane, seeps slowly upward through the sediment from deep geological sources. These cold seeps, as they are called, support communities that in some respects resemble hydrothermal vent communities but differ in important ways. The organisms here can be extraordinarily long-lived. Certain species of clam found at cold seeps in the Gulf of Mexico have been aged at more than 250 years, among the oldest animals ever recorded. The pace of life at a cold seep is calibrated to the slow, steady release of methane from the sediment below. Where a hydrothermal vent might erupt and collapse in years or decades, a cold seep can persist for thousands of years, supporting communities of stunning patience and longevity. Deep-sea fish have evolved extraordinary adaptations to life in darkness. Below about 200 meters, sunlight fades to a blue twilight, and below 1,000 meters, it is essentially gone entirely. The animals that live in this permanent darkness have evolved over millions of years to cope with conditions that are alien to surface life. Crushing pressure, near-freezing temperatures, scarcity of food, and an absence of light. Many deep-sea fish have enormous eyes, tuned to detect the faintest traces of bioluminescent light produced by other organisms. Others have no eyes at all, having lost them over evolutionary time as a costly organ no longer needed. Many are almost completely transparent, their internal organs visible through their bodies. Others are jet black, absorbing every photon in an environment where being seen means being eaten. The bodies of deep-sea fish often contain a high proportion of water and very little dense muscle, an adaptation that reduces the energy cost of maintaining buoyancy at depth without a swim bladder. Bioluminescence is the primary source of light in the deep ocean. Below the sunlit zone, the dominant form of light is not sunlight but bioluminescence, light produced by living organisms through chemical reactions within their own tissues. It is estimated that more than 75% of deep-sea animals produce bioluminescence of some kind, making it one of the most common biological phenomena on Earth. The functions of bioluminescence in the deep sea are varied. Some animals use it to attract prey, dangling a glowing lure in front of a mouth full of teeth, as the anglerfish does. Others use it to communicate with potential mates. Some use counter-illumination, glowing on their undersides to match the faint light filtering from above, making them invisible to predators looking upward. A few species produce bioluminescent mucus that they release as a decoy, leaving a glowing cloud to confuse a predator while they escape into the darkness. The anglerfish is one of the most unusual predators on Earth. In the deepest parts of the ocean, the anglerfish has evolved a hunting strategy with no parallel in the animal world. A bioluminescent lure, called an esca, hangs from a modified spine on the fish's head, dangling in front of its mouth like a living fishing rod. The light attracts prey in the darkness, drawing other animals close enough to be swallowed. The anglerfish's mouth is enormous relative to its body, and its stomach can expand to accommodate prey larger than itself, an adaptation to a food-scarce environment where any meal must be fully exploited. In many species, the female anglerfish is many times larger than the male. When the tiny male finds a female, he bites into her body and fuses to her permanently, his circulatory system connecting to hers. Over time, his eyes and fins degenerate, and he becomes functionally part of her body, providing sperm in exchange for the nutrients that keep him alive. It is a form of parasitism and partnership so extreme it has no close equivalent anywhere else in the animal kingdom. The abyssal plain is the largest habitat on Earth. Below about 4,000 meters, the ocean floor flattens into the abyssal plain, a vast expanse of nearly level seafloor covered with fine sediment accumulated over millions of years. These plains cover roughly half the Earth's total surface area, making them by far the most extensive habitat on the planet. Despite their enormous extent, they support far less life than the shallower continental shelves and slope areas, because very little organic matter survives the long journey down from the sunlit surface waters. What does arrive? Dead plankton, marine snow, fragments of larger organisms, is the foundation of the abyssal food web. Animals here have adapted to extreme food scarcity. Some sea cucumbers crawl across the mud, ingesting it to extract whatever organic material it contains. Others extend feeding arms into the water column to catch particles drifting past. Life at the abyss is patient and minimal, calibrated to the trickle of energy that arrives from above. Marine snow is the constant slow drift of organic particles from the surface to the deep. The deep ocean is fed almost entirely by a gentle, continuous rain of tiny particles from above, collectively known as marine snow. These particles, dead phytoplankton, bacterial cells, the shed skins and fecal pellets of zooplankton, fragments of dead animals, and aggregates of organic material, are typically less than a millimeter in size and drift downward so slowly that they can take weeks to reach the seafloor. As they sink, they are continuously consumed and degraded by bacteria and small animals, so only a tiny fraction of what is produced at the surface ultimately reaches the deep seafloor. Marine snow is the primary channel through which carbon fixed by photosynthesis at the surface is transported to the deep ocean, where some of it is permanently sequestered in sediments, an important part of the ocean's role in regulating atmospheric carbon dioxide. The pressure at great depths is extreme in ways that reshape living matter. At the bottom of the Mariana Trench, the pressure is approximately 1,086 atmospheres, more than 1,000 times the pressure at sea level. This pressure is not merely a physical challenge, it is a chemical one. At such pressures, the membranes of living cells, the shapes of proteins, and the function of enzymes are all affected. Cell membranes tend to become more rigid under pressure, which can impair their function. Enzymes can change shape, losing their ability to catalyze the reactions that life depends on. Deep-sea organisms have evolved specific molecular solutions to these problems. They produce proteins with different structures that remain functional under pressure. They modify the composition of their cell membranes to maintain the right degree of fluidity. Some produce small molecules called piezolites, depth-specific solutes. that stabilize proteins against pressure-induced distortion. The biochemistry of deep-sea life is subtly but profoundly different from that of surface life. Trenches are the deepest and least explored regions of the ocean. The deep-sea trenches, long, narrow depressions in the seafloor formed where one tectonic plate slides beneath another in the process called subduction, are the planet's most extreme environments. The Mariana Trench is the best known, but there are many others: the Tonga Trench, the Philippine Trench, the Japan Trench, the Kermadec Trench. Each is a different world with a distinct community of organisms shaped by its particular depth, water chemistry, and geological setting. Because trenches are so deep, so inaccessible, and so far from any continental shelf, they receive very little organic material from above. Yet they are not lifeless. A variety of amphipods, small crustaceans related to beach hoppers, have been found in the deepest trenches at densities that surprised researchers. Snailfish, which are vertebrates related to ordinary coastal fish, have been recorded at depths greater than 8 kilometers, making them the deepest living vertebrates ever observed. Subduction carries material from the ocean floor back into the Earth's interior. The ocean floor does not accumulate indefinitely. At subduction zones, where one tectonic plate dives beneath another, the oceanic crust, along with the sediments and water it carries, is pulled back down into the mantle. There it is subjected to enormous heat and pressure, melting and chemically transforming as it sinks. Some of this material rises again as magma, feeding the chains of volcanoes that typically form above subduction zones. The volcanic arcs of the Pacific Ring of Fire, the Andes, the Cascades. Subduction is not a clean process. As the descending plate sinks, it carries water that lowers the melting point of the surrounding mantle, triggering additional melting. The volatile compounds released, water, carbon dioxide, sulfur, rise into the overriding plate, driving the volcanism that has shaped so much of the world's geography. The ocean floor is a temporary surface. Its final destination is the interior of the planet. Tectonic plates move continuously, reshaping the ocean floor over millions of years. The solid outer layer of the Earth is divided into about a dozen major tectonic plates and several smaller ones, all moving relative to each other at speeds of a few centimeters per year. Over geological time, these movements have opened and closed ocean basins, brought continents together and pulled them apart, raised mountain ranges, and triggered earthquakes and volcanic eruptions. The Atlantic Ocean, for example, did not exist 200 million years ago. It has opened as the Americas drifted away from Europe and Africa. The Pacific Ocean, by contrast, is shrinking as subduction zones consume its floor along its margins. In hundreds of millions of years, the arrangement of ocean basins on Earth will be entirely different from what it is today. The ocean floor is not a fixed backdrop. It is a surface in continuous slow motion, driven by heat rising from the interior of the planet. Earthquakes on the seafloor can generate tsunamis of devastating power. When tectonic plates shift suddenly at a subduction zone, the seafloor can move vertically by several meters across an area of thousands of square kilometers. This movement displaces an enormous volume of water, generating waves, tsunamis, that radiate outward in all directions at the speed of a jet aircraft. In the open ocean, these waves are barely detectable, perhaps 30 centimeters in height, spread over a wavelength of hundreds of kilometers. But as they approach shallow coastal waters, the shallowing seafloor forces the wave's energy upward, dramatically increasing its height. The 2004 Indian Ocean tsunami, triggered by a magnitude 9.1 earthquake off the coast of Sumatra, generated waves that reached 30 meters in height in some locations and caused devastation across more than a dozen countries. The energy released in that earthquake was equivalent to the power consumption of the entire United States for several months. It began with a movement of the seafloor that lasted about 8 minutes. Seamounts are underwater mountains that rise from the ocean floor but do not reach the surface. Scattered across the ocean floor are thousands of seamounts, isolated underwater mountains of volcanic origin, most of them extinct, rising hundreds or thousands of meters from the surrounding seafloor without reaching the surface. Where seamounts approach the surface, they can deflect deep ocean currents upward in a process called upwelling, bringing cold, nutrient-rich water toward the light and creating conditions for unusually productive marine ecosystems. The seamount's hard surface provides attachment points for corals, sponges, and other sessile organisms in a habitat otherwise dominated by soft sediment. Over millions of years, a seamount can subside as the ocean floor beneath it gradually cools and contracts, eventually sinking below the surface of the seafloor itself and becoming a flat-topped feature called a guyot. The Hawaiian Islands are the currently visible tips of a chain of seamounts produced by a hotspot, a fixed plume of unusually hot mantle rising through the overlying plate. Deep-sea sediments are archives of Earth's climate history. The soft sediment that blankets much of the ocean floor is not simply mud. It is a stratified record of everything that has fallen through the water column over millions of years. The shells of microscopic plankton, wind-blown dust from distant continents, volcanic ash from ancient eruptions, fragments of cosmic material that arrived as micrometeorites. By extracting cylindrical cores from the sediment and analyzing the material layer by layer, scientists can read climate history across spans of time that dwarf all of human civilization. The ratio of oxygen isotopes in the shells of ancient foraminifera, microscopic single-celled organisms whose shells accumulate in vast quantities on the seafloor, records the temperature of the seawater in which they lived. Cycles of ice ages and warm periods over the past millions of years are preserved in these shells with extraordinary detail. The seafloor is Earth's most complete diary. Foraminifera are microscopic organisms whose shells build much of the deep-sea sediment. Foraminifera, commonly called forams, are single-celled organisms, most smaller than a millimeter, that secrete shells of calcium carbonate in an enormous variety of shapes: spirals, discs, spheres, chains. They live throughout the ocean water column, and when they die, their shells drift downward to the seafloor. Over millions of years, these shells accumulate in layers of remarkable thickness. In some parts of the ocean, the sediment is composed almost entirely of foraminiferal shells, a material called foram ooze, to depths of hundreds of meters. Because different species of foraminifera lived at different times in the past and under different climate conditions, the species composition of a sediment layer is a precise indicator of the age and environmental conditions at the time of deposition. Foram shells are among the most powerful tools in paleoclimate science. Methane hydrates are a frozen form of natural gas locked in the seafloor sediment. In the cold, high-pressure environment of the deep seafloor, methane gas can combine with water molecules to form a solid crystalline compound called methane hydrate, a substance that looks like dirty ice and burns when lit, because the methane it contains is released when it is brought to lower pressures. Vast quantities of methane hydrates are stored in seafloor sediments along continental margins around the world. The total amount of carbon locked in these deposits may exceed all known reserves of conventional fossil fuels. They are of interest both as a potential energy resource and as a climate concern. If warming ocean temperatures were to destabilize large quantities of methane hydrates, the released methane, a powerful greenhouse gas, could accelerate warming in a feedback loop. They are also geologically hazardous. The destabilization of hydrate layers can trigger underwater landslides of enormous scale. Underwater landslides can move enormous volumes of sediment across the seafloor. The slopes of the continental margins, the areas where the relatively shallow continental shelves drop away toward the deep ocean floor, are not always stable. When sediment accumulates faster than it can compact, when earthquake shaking destabilizes a slope, or when methane hydrate layers melt and lose their structural strength, the result can be an underwater landslide or submarine mass movement of staggering scale. The Storegga slide off the coast of Norway, which occurred approximately 8,200 years ago, involved the collapse of a section of seafloor roughly the size of Iceland, moving hundreds of kilometers across the ocean bottom. The tsunami it generated was estimated to have reached heights of 20 meters or more along the coasts of what are now Scotland and Norway. These events are rare on human timescales, but common in geological terms, and their deposits, recognizable layers of chaotically mixed sediment called debrites, are found on continental slopes around the world. Turbidity currents are underwater avalanches of sediment. When a large mass of sediment on a continental slope becomes destabilized, it can transform into something more fluid than a landslide. A turbidity current, a dense, fast-moving mixture of sediment and seawater that can flow down the slope and across the abyssal plain at speeds of tens of kilometers per hour, traveling hundreds of kilometers before its energy is spent. These currents carve submarine canyons into continental slopes, deposit characteristic layers of sediment called turbidites on the abyssal plain, and can destroy seafloor infrastructure. Submarine cables have been snapped by turbidity currents, their timing used by scientists to reconstruct the speed and path of the current. The largest turbidite deposits known cover areas the size of entire countries, laid down in single events that would have been among the most powerful geological processes on Earth at the time they occurred. Submarine canyons cut deep valleys into the continental slopes. Among the most impressive features of the continental margins are submarine canyons. Deep, steep-sided valleys eroded into the continental slope, often extending from the edge of the continental shelf down to the abyssal plain. Some of the largest are comparable in scale to the Grand Canyon. The Hudson Canyon, extending from the mouth of the Hudson River off the coast of New York, runs for more than 700 kilometers across the continental shelf and slope before reaching the abyssal plain. These canyons were carved partly by turbidity currents and partly, in some cases, by rivers during periods of low sea level when the continental shelves were exposed as dry land. They are now important conduits for transporting organic material from the continental shelves into the deep ocean, and they support unusually rich communities of deep-sea life along their walls and floors. Deep-sea corals build slow-growing reefs in complete darkness. When most people think of coral reefs, they picture warm, shallow, sunlit waters filled with color and movement. But corals also exist in the deep sea, cold water corals that need no sunlight and live at depths ranging from a few hundred to several thousand meters. These corals grow extraordinarily slowly. Some colonies have been dated at several thousand years old. They build three-dimensional reef structures that provide habitat for a rich community of fish, invertebrates, and other organisms in an environment that would otherwise be dominated by soft sediment. Deep-sea coral reefs are among the most biodiverse habitats in the deep ocean. They are also extraordinarily vulnerable. A single pass of a bottom trawl can destroy in minutes what took thousands of years to build, and recovery, if it occurs at all, unfolds over timescales far beyond any human planning horizon. Giant deep-sea sponges filter enormous volumes of water. In some areas of the deep ocean, particularly on the continental slopes and on seamounts, the seafloor is dominated not by corals but by sponges, sometimes enormous ones. Some species of deep-sea sponge can grow to 2 meters in height and live for thousands of years, making them among the longest-lived animals on Earth. A single large sponge can filter thousands of liters of seawater per day, removing bacteria and organic particles and releasing clean water. Fields of deep-sea sponges function as ecosystem engineers, altering the flow of water and the distribution of food across large areas of the seafloor. The silica skeletons that many deep-sea sponges build, structures of extraordinary geometric elegance, remain on the seafloor long after the animal dies, providing a hard surface for other organisms to colonize in an environment otherwise dominated by soft mud. Whale falls create temporary oases of life on the deep seafloor. When a whale dies in the open ocean, its body sinks slowly toward the seafloor. In the water column, it is consumed by scavenging fish and other mobile organisms. When what remains reaches the bottom, often after several months, it becomes something extraordinary, a concentrated source of organic material in an environment where food is normally extremely scarce. The process of consuming a whale carcass on the seafloor unfolds in stages over decades. First, mobile scavengers arrive: sleeper sharks, hagfish, and crustaceans that strip the soft tissue from the bones over months. Then mat-forming bacteria colonize the remains, and with them come polychaete worms and other invertebrates that feed on the bacterial mats. Finally, once the soft tissue is gone, a community of specialist organisms feeds on the lipid-rich bones themselves, including a remarkable group of polychaete worms called ostacs, which bore into the bone with root-like extensions and host bacteria that digest the bone's oils. A single large whale can support communities of organisms for 50 to 100 years, a slow feast in the dark. Hadal zone animals have evolved unique biochemical solutions to extreme pressure. The hadal zone, the deepest parts of the ocean, below 6,000 meters, is home to a surprising diversity of life that has adapted over millions of years to conditions impossible for surface animals to survive. The amphipods that dominate the hadal zone in terms of abundance are crustaceans related to beach hoppers and freshwater shrimp, but adapted in numerous ways to life at the extreme. Their cell membranes contain a higher proportion of unsaturated fatty acids, which remain more fluid under high pressure. Their enzymes are structurally modified to function correctly at pressures that would denature the equivalent enzymes from surface animals. Their bodies accumulate trimethylamine oxide, a compound that counteracts the pressure-induced distortion of proteins. These biochemical adaptations are not random. They are the result of millions of years of selection in an environment that ruthlessly eliminates any organism whose chemistry cannot cope. The seafloor's magnetic stripes were key evidence for plate tectonics. In the mid-20th century, ships conducting magnetic surveys of the ocean floor discovered something puzzling. The basalt of the seafloor showed alternating bands of normal and reversed magnetic polarity, running parallel to and symmetrically on either side of the mid-ocean ridge. This pattern was explained by the process of seafloor spreading. As new basalt formed at the ridge and solidified, it recorded the direction of Earth's magnetic field at the time. Since Earth's magnetic field periodically reverses, north becomes south and south becomes north, the newly formed seafloor preserved a striped record of these reversals, spreading outward from the ridge like a magnetic tape recording. This discovery was critical evidence for plate tectonics, demonstrating conclusively that the seafloor was moving away from the ridge at measurable rates, and providing a way to date ocean floor of different ages by comparing its magnetic signature to the known chronology of magnetic reversals. Ocean sediment cores have revealed past periods of rapid climate change. Among the most important findings from the analysis of deep-sea sediment cores has been the discovery that Earth's climate has not always changed slowly and gradually. Within individual sediment cores, there are layers that record abrupt and dramatic shifts in temperature and ocean chemistry occurring over periods as short as a few decades or centuries. Rapid by geological standards. The Dansgaard-Oeschger events, for example, were rapid warmings of the North Atlantic region that occurred repeatedly during the last ice age, each unfolding over as little as a few decades and involving temperature increases of 10 degrees Celsius or more. The sediment cores that record these events do so in precise detail, preserving in their foraminifera and chemical composition a faithful record of conditions at the sea's surface thousands of years ago. The ocean floor remembers what the atmosphere cannot. Deep-sea microbes are among the most abundant organisms on Earth. The sediment of the deep ocean floor is not merely a chemical and geological archive, it is alive. Microbial life extends meters into the seafloor sediment, persisting in conditions of extreme cold, high pressure, negligible energy, and near total isolation from the surface world. The cells in these sediments are alive, but they exist in a state of almost incomprehensible slowness. Some microbial populations in deep seafloor sediments are estimated to divide only once every 1,000 years, or even less frequently. Despite this near-suspended animation existence, they are metabolically active, slowly processing organic matter and cycling nutrients in ways that influence ocean chemistry over geological time spans. The total mass of microbial life in deep-sea sediments may rival or exceed the combined mass of all life on the ocean's surface, an entire biosphere hidden in the mud. The deep ocean plays a critical role in regulating Earth's climate. The ocean's role in the global climate system extends far beyond absorbing solar heat. The deep ocean acts as a long-term reservoir for heat, carbon dioxide, and other climatically important substances. When carbon dioxide dissolves in seawater, much of it eventually sinks to the deep ocean as part of the biological carbon pump, the process by which photosynthesizing organisms in the surface ocean fix carbon and, when they die, carry it downward as their bodies sink. At depth, this carbon is effectively removed from the atmosphere for hundreds to thousands of years. The deep circulation of the ocean, the global conveyor belt of cold, dense water that sinks in the North Atlantic, flows along the seafloor toward the Antarctic, and slowly rises again in the Pacific and Indian Oceans, distributes this stored carbon and heat around the planet on timescales of centuries to millennia. Changes in this circulation can have profound consequences for global climate. The thermohaline circulation moves cold, salty water around the entire planet. Deep within the ocean, a circulation system driven by differences in temperature and salinity moves water on a journey that spans all ocean basins and takes roughly 1,000 years to complete. In the North Atlantic, surface water that has been cooled by contact with cold air and has become saltier through evaporation becomes dense enough to sink to the deep ocean. This water then flows southward along the ocean floor, eventually making its way around Antarctica and spreading northward into the Pacific and Indian Oceans, where it gradually warms and rises back to the surface. This system, called the thermohaline circulation or the global ocean conveyor belt, distributes heat from the tropics toward the poles, keeps Europe warmer than it would otherwise be at its latitude, and moves enormous quantities of dissolved oxygen and nutrients to the deep ocean. Its disruption, which could occur if melting ice dilutes the salty surface water of the North Atlantic, is one of the most significant potential consequences of rapid climate warming. Oxygen minimum zones create dead zones in the midwater column. In some parts of the ocean, particularly at depths between 200 and 1,000 meters in the eastern Pacific and the northern Indian Ocean, dissolved oxygen levels drop to near zero in a region called the oxygen minimum zone. This occurs where the decomposition of sinking organic matter consumes oxygen faster than it can be replenished by circulation. Within these zones, most animals cannot survive, and the seafloor beneath them can be covered with mats of sulfur-oxidizing bacteria rather than the more diverse communities found elsewhere. As the ocean warms and absorbs more carbon dioxide, oxygen minimum zones are expanding, a change with significant consequences for the distribution of marine life and for the chemistry of the deep ocean. They are also of paleoclimate interest. During past warm periods, oxygen minimum zones were sometimes so extensive that seafloor sediments beneath them were entirely devoid of oxygen, preserving organic matter in exquisite detail instead of allowing it to decompose. Manganese nodules litter large areas of the abyssal plain. On the flat sediment plains of the deep ocean, particularly in the Pacific, lie vast fields of dark, lumpy objects about the size of potatoes. These are manganese nodules, concretions of manganese, iron, nickel, cobalt, and copper that grow around a small nucleus, accumulating layer by layer from minerals dissolved in the seawater and sediment-poor water. The process is extraordinarily slow. A nodule might grow by a millimeter over 1 million years, making these objects among the slowest growing natural structures on Earth. Many nodules that litter the Pacific abyssal plain today began forming tens of millions of years ago, because they are rich in metals that are increasingly important for modern technology. Nickel and cobalt in particular are critical components of electric vehicle batteries. There is substantial commercial interest in mining them. The ecological consequences of doing so are a matter of significant scientific and ethical concern. The seafloor hosts unique geological features called mud volcanoes. In addition to the volcanic activity associated with the mid-ocean ridge and subduction zones, the deep seafloor has another, stranger form of geological feature: mud volcanoes. These are structures formed when pressurized fluids, water, gases, and fluidized sediment from depth are forced upward through overlying sediment, erupting at the surface as flows of mud, brine, and gas. Unlike true volcanoes, mud volcanoes are not powered by magma. They are found primarily along convergent margins, where sediment is squeezed by the compression of converging plates, and along continental margins where large quantities of gas are generated by organic matter decomposing in the sediment. Some mud volcanoes support chemosynthetic communities similar to those found at cold seeps. Others release methane in significant quantities. Hundreds are known in the deep sea. Many more remain undiscovered. Hydrothermal vent minerals create natural chemical gradients that may have been important for the origin of life. Beyond their importance as ecosystems, hydrothermal vents have attracted intense interest from scientists studying the origin of life on Earth. Some alkaline hydrothermal vents, a different type from the hot, acidic black smokers, produce tiny mineral chambers with walls that separate fluids of different chemistry, creating natural electrochemical gradients across those walls. These gradients bear a remarkable resemblance to the proton gradients that drive energy generation in living cells. The theory that life may have first emerged in structures like these, using the natural chemistry of the vent to power the first self-replicating molecules, is currently one of the most actively researched hypotheses in origins of life science. The first living cell may not have assembled itself in a warm little pond, as Darwin once speculated, but in the mineral chambers of a hydrothermal vent on the ancient ocean floor. Iron fertilization of the ocean affects the biological carbon pump. Phytoplankton, the microscopic photosynthesizing organisms that form the base of the ocean food web, require iron to grow. In vast regions of the ocean, particularly the Southern Ocean around Antarctica, phytoplankton growth is limited not by sunlight or by the availability of major nutrients like nitrogen and phosphorus, but by the scarcity of dissolved iron. Iron reaches the surface ocean primarily through wind-blown dust from continental deserts and through upwelling of deep water that has absorbed iron from seafloor sediments. During past ice ages, when dust transport was much greater, iron fertilization of the Southern Ocean was enhanced, driving increased phytoplankton growth, increased carbon uptake, and lower atmospheric carbon dioxide. This relationship between iron, phytoplankton, and atmospheric carbon has made iron fertilization, the deliberate addition of iron to the ocean to stimulate carbon uptake, a controversial proposed geoengineering strategy. The seafloor's chemistry connects to the atmosphere in ways that are still being fully traced. The continental shelves are the most productive regions of the ocean. Although they cover only about 8% of the ocean's total area, the continental shelves, the shallow, gently sloping areas between the shoreline and the edge of the deep ocean floor, account for a disproportionately large share of the ocean's total biological productivity. The combination of shallow water, which brings sunlight to the seafloor, the proximity of nutrient-rich terrestrial runoff, and the upwelling of deep water along shelf edges creates conditions ideal for phytoplankton growth and cascading upward through the food web for fish, marine mammals, and seabirds. The world's major fisheries are overwhelmingly concentrated on the continental shelves. The deeper ocean floor, despite its enormous extent, supports far less life per unit area, a consequence of the scarcity of both light and nutrients in the deep. Deep-sea mining poses significant risks to fragile ecosystems that recover slowly. The minerals found on and beneath the deep ocean floor, manganese nodules, cobalt-rich crusts on seamounts, seafloor massive sulfides at hydrothermal vents, have attracted growing commercial interest as terrestrial supplies of critical metals are depleted or become more difficult to access. But the deep-sea environments that host these minerals are extraordinarily fragile. The animals that live on manganese nodules, for example, are associated with the hard surfaces the nodules provide in an environment otherwise dominated by soft mud. Remove the nodules, and these animals lose their habitat. The sediment plumes raised by mining equipment can smother organisms across large areas and may persist in the water column for months. Recovery from significant physical disturbance in the deep ocean, where growth and reproduction are extremely slow, is measured not in years but in decades to centuries. The areas disturbed by seafloor mining experiments conducted in the 1970s show little recovery more than 50 years later. Plastic pollution has reached the deepest parts of the ocean. The contamination of the ocean by plastic waste is not limited to the floating patches of debris at the surface or the accumulation on coastal shores. Plastic has reached the deep ocean, including the very deepest trenches. Microplastics, fragments smaller than 5 millimeters, produced by the breakdown of larger plastic items, have been found in deep-sea sediments around the world at concentrations that in some places exceed those on the ocean surface. Amphipods collected from the Mariana Trench were found to contain plastic in their bodies. A plastic bag was observed at the bottom of the Mariana Trench, more than 10 kilometers below the surface, in 2019. Once plastic sinks to the deep ocean or is incorporated into seafloor sediment, it is effectively removed from any possibility of cleanup. The deep ocean is not a remote and protected wilderness. It is a sink for the consequences of surface activity. bioluminescent organisms create displays of light visible from submarines. For those who have had the rare opportunity to descend in a submersible into the deep ocean at night, with all lights turned off, the experience is often described as one of the most extraordinary of their lives. The surrounding darkness is not empty. It is alive with points and flashes and pulses of light produced by organisms moving through the water. Jellyfish trail glowing tentacles. Dinoflagellates, microscopic plankton, flash when disturbed. Fish flash patterns of light along their sides. Bioluminescent bacteria drift in glowing clouds. Some researchers estimate that bioluminescence is visible to the human eye throughout the water column in the deep ocean on any given night, a continuous light show powered entirely by living chemistry. It is one of the most beautiful environments on Earth and one of the least seen. The Juan de Fuca Ridge is one of the most intensively studied parts of the seafloor. Off the coast of the Pacific Northwest of North America, a section of the mid-ocean ridge called the Juan de Fuca Ridge has been the subject of intensive scientific study for decades. It is relatively close to North American research institutions, accessible to repeated expeditions, and hosts a variety of hydrothermal vent systems, active volcanic features, and seafloor observatories. Cabled observatories on the Juan de Fuca Ridge connect sensors on the seafloor to onshore laboratories via underwater fiber optic cables, transmitting continuous data on seismic activity, temperature, pressure, water chemistry, and biological activity. These observatories have captured the real-time signatures of submarine volcanic eruptions, detected the precursors of events at hydrothermal vents, and recorded the passage of earthquakes through the seafloor in unprecedented detail. They represent the frontier of what is possible when the deep ocean is connected to the surface world in real time. Ancient ocean crust preserves a record of past conditions on Earth. The oldest ocean floor that still exists, about 340 million years old, found in the Mediterranean and the Western Pacific, preserves a record of conditions that cannot be obtained from any other source. The chemistry of the ancient basalt records the temperature and composition of the seawater through which it cooled. The sediments above it record biological and chemical conditions in the ocean across hundreds of millions of years. The magnetic stripes record the history of Earth's magnetic field reversals. Taken together, Old Ocean Crust is a multi-channel archive of planetary conditions across geological time, a record of the ocean's temperature, acidity, oxygen content, biological productivity, and chemical composition stretching back hundreds of millions of years. It is impermanent. It will eventually be subducted and destroyed, but while it exists, it is one of the richest geological records available to science. Some deep-sea creatures travel vast vertical distances daily. Life in the ocean is not stationary. Many organisms perform daily vertical migrations of hundreds of meters, ascending toward the surface at night to feed on the abundant plankton there, then descending again before dawn to escape the visual predators that hunt in lit water. These vertical migrations are among the largest animal movements on Earth, involving enormous numbers of individuals crossing vast distances every 24 hours. They also play a significant ecological and biogeochemical role. Organisms that feed near the surface and then descend carry organic carbon with them, effectively transporting it from the upper ocean to depth and releasing it through respiration and excretion. This biological transport of carbon, called the active transport component of the biological carbon pump, is a meaningful contributor to the ocean's capacity to sequester carbon from the atmosphere. Serpentinization produces hydrogen on the seafloor and may fuel chemosynthetic life. In some areas of the deep seafloor, particularly where the lower layers of the oceanic crust are exposed to seawater through faulting and fracturing. A chemical reaction called serpentinization takes place. When seawater contacts certain iron and magnesium-rich rocks, it reacts with them, altering their mineralogy and releasing hydrogen gas and heat. The hydrogen released by serpentinization can serve as an energy source for hydrogen-oxidizing bacteria, supporting chemosynthetic communities in the absence of any volcanic activity. The Lost City hydrothermal vent field, discovered in 2000 at a site in the Atlantic Ocean far from any spreading center, is powered by serpentinization rather than by volcanic heat. Its chimneys, white, calcium carbonate structures up to 60 meters tall, are among the most striking features ever seen on the deep sea floor. Lost City may also be particularly relevant to the origin of life. The chemistry it produces is in some ways more promising as a cradle for life than the hot, acidic environment of black smokers. The seafloor of the Arctic Ocean is less well mapped than the surface of Mars. Despite being surrounded by countries with advanced scientific programs, the seafloor of the Arctic Ocean remains extraordinarily poorly understood. The permanent or seasonal ice cover makes ship-based surveys difficult. The extreme remoteness adds logistical challenges. The political sensitivities around Arctic sovereignty and resources complicate research access. As a result, large swaths of the Arctic seafloor are known only from sparse acoustic surveys conducted by military submarines or from brief, seasonal research expeditions. The detailed topography of the Arctic seafloor, its ridges, basins, seamounts, and sediment deposits, is in many areas known less precisely than the equivalent areas of the lunar surface or Mars. The melting of Arctic sea ice, a consequence of climate warming, is opening some of these areas to more intensive survey for the first time. What that increased access reveals will be among the most significant additions to our knowledge of the seafloor in decades. Deep-sea life cycles are often governed by pulses from the surface. The deep ocean may seem isolated from the surface world, but it is not. The biology of the deep seafloor is profoundly influenced by what happens far above it. Seasonal blooms of phytoplankton at the surface, triggered by warming temperatures and increasing daylight in spring, produce pulses of organic material that sink to the seafloor weeks later as accelerated marine snow. Deep-sea organisms track these pulses. Sea cucumbers time their reproduction to the arrival of food from above. Microbial communities in the sediment respond to changes in the quality and quantity of organic matter that reaches them. Even the behavior of deep-sea fish can shift seasonally in response to changes in the food supply from the surface. The deep ocean breathes in rhythm with the surface, connected by gravity and by the slow drift of particles through kilometers of water. What happens at the surface of the ocean matters, eventually, all the way to the bottom. The lost continent of Zealandia lies mostly submerged beneath the southwestern Pacific Ocean. Among the least widely known geological features on Earth is Zealandia, a fragment of continental crust that broke away from Australia roughly 80 million years ago and subsequently sank almost entirely beneath the Pacific Ocean. Only a small fraction of Zealandia now stands above sea level, forming the islands of New Zealand and New Caledonia. The rest, an area roughly half the size of Australia, lies between 1,000 and 3,000 meters below the surface. In 2017, the scientific community formally recognized Zealandia as Earth's eighth continent, on the basis of its continental crust composition, its elevation relative to the surrounding oceanic crust, and its geological distinction from the Australian plate. Much of its seafloor remains unmapped in detail, and the ecological communities of its sunken margins are largely unexplored. Hydrothermal vent communities are found in isolated patches separated by vast distances. Unlike the continuous ecosystems of the surface world, hydrothermal vent communities are isolated oases separated by hundreds or thousands of kilometers of cold, dark, inhospitable seafloor. The organisms living at one vent field cannot simply walk or swim to the next. The distances are too great and the conditions of the open, deep seafloor too hostile. Yet many vent species are found at multiple widely separated locations, suggesting that their larvae must be capable of dispersal across these vast distances, carried by deep ocean currents on journeys of weeks or months. How larvae survive these crossings, what they eat, how they detect a new vent, how they settle and establish themselves, are questions that remain only partially answered. The connectivity of vent communities across ocean basins is a fascinating problem in deep-sea biogeography, with implications for understanding how isolated populations evolve and diverge. Sound travels exceptionally well through the deep ocean. In the deep ocean, there is a layer of water at a depth of roughly 600 to 1,200 meters where temperature and pressure interact to create a channel of minimum sound speed. Sound waves entering this channel are refracted toward it from above and below, trapping acoustic energy within the channel and allowing it to travel extraordinary distances with very little loss. This feature of the ocean, called the SOFAR Channel, was exploited by the United States military during the Cold War to listen for submarines across entire ocean basins. It is also used by marine animals. Blue whales and other large cetaceans communicate at frequencies and volumes that allow their calls to travel through the SOFAR channel for thousands of kilometers. The deep ocean is not silent. It carries the voices of the largest animals on Earth across entire ocean basins, in a communication channel that evolved hundreds of millions of years before humans learned to use it. Seafloor spreading rates vary significantly in different ocean basins. Not all mid-ocean ridges spread at the same rate. In the Atlantic Ocean, seafloor spreading is relatively slow, a few centimeters per year, and the ridge is narrow and rugged, with a prominent central rift valley. In the Eastern Pacific, the East Pacific rise spreads much more quickly, up to 15 centimeters per year at its fastest, and the ridge is correspondingly broader and less rugged, with less prominent topography. These differences in spreading rate affect the geology and biology of the ridge. Fast-spreading ridges erupt more frequently and maintain more continuous hydrothermal activity, while slow-spreading ridges have longer intervals between eruptions and more complex faulted terrain. The rate of seafloor spreading also determines how quickly the ocean basin expands. The Atlantic is growing. The Pacific is shrinking. In a few 100 million years, the arrangement of ocean basins on Earth will be entirely different. The ocean floor is divided into distinct depth zones, each with its own character. Scientists who study the ocean organize its depth into a series of zones, each with distinct physical conditions and biological communities. The sunlit epipelagic zone extends from the surface to about 200 meters, where light is sufficient for photosynthesis. Below it, the mesopelagic or twilight zone stretches to about 1,000 meters, receiving traces of light but none sufficient for plant growth. The bathypelagic zone extends from 1,000 to 4,000 meters, in complete darkness and near freezing cold. The abyssal zone covers the ocean floor between 4,000 and 6,000 meters, the vast flat plains that dominate the seafloor. And below 6,000 meters lies the hadal zone, found only in the deepest trenches. Each zone is a world unto itself, with organisms found nowhere else, adapted over millions of years to its particular combination of pressure, temperature, darkness, and food supply. Sonar technology revolutionized our understanding of the seafloor's shape. Before the development of sonar in the 20th century, the depth of the ocean floor could only be measured by lowering a weighted rope or wire to the bottom, a process so slow that the positions of individual measurements were separated by many kilometers. The invention of echo-sounding sonar in the 1920s allowed ships to measure depth continuously as they moved, producing the first real profiles of the seafloor's topography. By the 1950s, systematic sonar surveys began revealing the mid-ocean ridge, the deep trenches, and the general architecture of the ocean basins for the first time. Modern multi-beam sonar systems, which simultaneously measure depth across a wide swath of seafloor, have dramatically accelerated the mapping process. But even so, the ocean floor remains one of the least surveyed surfaces on Earth. The tools have transformed. The scale of the task has not. Hydrothermal vent communities were predicted before they were found. In the years before their discovery in 1977, some oceanographers had speculated about what might be found at the sites where the mid-ocean ridge met the cold, deep ocean. The presence of hydrothermal circulation had been inferred from temperature anomalies in the water column above ridge crests, and the chemistry of vent fluids had been theorized based on chemical imbalances in seawater. But the lush biological communities that surrounded the actual vents, the tube worms, the giant clams, the dense mats of bacteria, were entirely unexpected. No scientific prediction had suggested that the deep sea could support ecosystems of this density in the complete absence of sunlight. The discovery required a fundamental revision of biology's understanding of where the boundaries of life lay and how energy could flow through an ecosystem without photosynthesis at its foundation. Seafloor hot springs exist in freshwater lakes, as well as in the ocean. Hydrothermal venting is not unique to the deep ocean. Similar systems exist in deep freshwater lakes, where the lake floor overlies volcanically active geology. Lake Baikal in Siberia, the world's deepest and oldest freshwater lake, hosts hydrothermal vents on its floor that support unique communities of organisms found nowhere else. Lake Tanganyika in Africa has similarly been found to harbor warm water venting in its deepest regions. These freshwater vent systems differ chemically from marine ones. They lack the high salinity and some of the mineral content of ocean vents, but they share the fundamental characteristic of providing chemical energy to biological communities in environments where sunlight cannot reach. They expand the catalog of places on Earth where chemosynthesis sustains life and add to the argument that hydrothermal systems may be among the most widespread and ancient energy sources for life on this planet. Deep currents can be tracked using chemical tracers dissolved in seawater. The circulation of water through the deep ocean is not directly visible. There are no waves, no whitecaps, no obvious indicators of flow in the darkness. Scientists track deep ocean currents using chemical fingerprints, specific combinations of temperature, salinity, dissolved oxygen, and trace chemicals that identify water masses formed in particular locations. Water that forms in the North Atlantic has a distinctive combination of high salinity and specific isotope ratios. Water that forms around Antarctica has its own signature. By mapping these chemical fingerprints across ocean basins, oceanographers can trace the paths that water follows as it sinks, spreads, and slowly rises again over centuries and millennia. Some of the water currently found at the bottom of the North Pacific last touched the surface in the North Atlantic over 1,000 years ago, before European contact with the Americas. Sea cucumbers dominate the biomass of many abyssal plain communities. In the sediment of the abyssal plain, where food is extremely scarce and life correspondingly sparse, one group of animals is surprisingly abundant: sea cucumbers, or holothurians. These soft-bodied, elongated animals process large volumes of sediment to extract the small amounts of organic material it contains, moving slowly across the mud like living vacuum cleaners. In some areas of the deep Pacific, sea cucumbers account for more than 90% of the visible animal biomass on the seafloor. Different species have evolved different strategies. Some crawl along the sediment surface. Others swim slowly through the water just above the bottom. Still others stand with one end raised into the water column, filtering passing particles. In an environment defined by scarcity, sea cucumbers have become the dominant large animals by finding ways to exploit the most abundant resource available, the thin layer of organic material mixed into the mud beneath their feet. The discovery of hydrothermal vents changed the search for life on other worlds. Before 1977, the search for extraterrestrial life was almost entirely focused on finding environments similar to Earth's surface: liquid water, access to sunlight, a suitable temperature range. The discovery that thriving ecosystems could exist in the absence of sunlight, powered instead by chemical energy, expanded the catalog of potentially habitable environments enormously. The moons of Jupiter and Saturn are now among the most actively considered targets in the search for extraterrestrial life. Europa, a moon of Jupiter, is thought to have a liquid water ocean beneath its icy surface, potentially in contact with a rocky seafloor where hydrothermal activity might occur. Enceladus, a moon of Saturn, actively vents water vapor and organic compounds from a subsurface ocean through cracks in its ice. The ocean floor of Earth has become a model not just for deep-sea biology, but for the kind of biology that might exist in the most unlikely environments elsewhere in the solar system. Submarine volcanoes produce eruptions that go largely undetected. An unknown but significant number of volcanic eruptions occur on the seafloor every year. Most are on the mid-ocean ridge, where magma rises continuously to fill the gap between separating tectonic plates. These eruptions typically produce lava flows that spread across the ridge crest, building new ocean floor from freshly solidified basalt. They can be detected by hydrophone networks, underwater microphones that detect the acoustic signals generated by lava cracking and flowing, and by changes in water temperature and chemistry above the eruption site. Occasional eruptions are detected in real time, allowing research vessels to reach the site within days and document the appearance of new seafloor and the colonization of the fresh lava surface by pioneer organisms. Most submarine eruptions, however, go completely unobserved, noticed only later from the record they leave in the magnetic properties and age of the basalt. The abyssal plain can experience biological booms following surface events. The deep seafloor is not entirely isolated from the immediate consequences of events above. When conditions at the surface of the ocean produce unusually large blooms of plankton, triggered by an influx of nutrients from river flooding, an unusual atmospheric event, or a seasonal upwelling of exceptional intensity, the resulting flood of organic material that sinks to the seafloor can produce a temporary biological boom in the deep. Sea cucumbers increase their feeding rate. Bacterial populations expand rapidly. Mobile scavengers congregate in areas of unusual food abundance. These pulses of productivity are temporary. The surface bloom fades, the organic rain slows again, and the deep seafloor returns to its baseline state of patient scarcity. But they illustrate how directly and rapidly events at the surface can affect communities in the deepest parts of the ocean. Fracture zones cut across the seafloor perpendicular to the mid-ocean ridge. The mid-ocean ridge is not a continuous, uninterrupted chain of spreading centers. It is offset at numerous locations by structures called transform faults. Essentially, large horizontal cracks in the seafloor along which the ridge segments are offset from each other, sliding in opposite directions. These transform faults extend beyond the ridge as fracture zones. Long, linear scars in the seafloor that can stretch for thousands of kilometers across the ocean basin, marking the trace of past and present plate motions. Some fracture zones are among the most prominent topographic features of the ocean floor, with walls dropping thousands of meters from the adjacent seafloor. They can deflect deep currents, create topographic barriers between ocean basins, and provide habitat for unique communities of organisms on their steep walls. The Romanche Fracture Zone in the equatorial Atlantic, for example, is one of the few deep connections between the eastern and western Atlantic basins. Giant isopods are among the most visually striking inhabitants of the deep seafloor. In the deep Atlantic, Pacific, and Indian Oceans, at depths between 170 and 2,140 meters, lives a creature that looks like something from a science fiction novel, the giant isopod, a crustacean related to the familiar pill bugs found in garden soil, but scaled up to lengths of more than 40 centimeters. Giant isopods are scavengers, feeding on the dead fish, whales, and other organic material that sinks to the seafloor. They are capable of consuming large amounts of food in a single sitting and then going without eating for extraordinary periods. Specimens in aquariums have survived without food for more than 5 years. Their large size relative to their terrestrial relatives is an example of deep-sea gigantism, a phenomenon observed in many groups of deep-sea invertebrates, thought to result from the combination of cold temperatures, high pressure, and the need to travel large distances between food sources in an environment where meals are infrequent. The seafloor has been used to dispose of chemical weapons after World War II. In the decades following World War II, thousands of tons of chemical weapons, artillery shells filled with mustard gas and other agents, as well as various chemical compounds, were dumped into the ocean by multiple nations, including the United States, the United Kingdom, Germany, and the Soviet Union. These materials were considered a convenient way to dispose of stockpiles that could not easily be destroyed on land. They now lie on the seafloor in various locations around the world, in various states of deterioration. In some areas, fishing vessels have inadvertently brought up corroded shells in their nets. The long-term ecological consequences of this contamination are not fully understood, and the practical challenges of surveying and potentially remediating these sites are enormous. The deep ocean has served, among its many roles, as a repository for some of the most difficult legacies of the 20th century. Some deep-sea organisms have extremely slow metabolisms that allow them to live for centuries. In the cold, food-poor environment of the deep ocean, the evolutionary pressure to maximize the use of available energy has produced organisms with metabolisms so slow they are almost unimaginable by the standards of surface life. The Greenland shark, which ranges into deep, cold waters, has been aged at over 400 years using radiocarbon dating of its eye lenses, making it the longest-lived vertebrate known to science. Deep-sea tube worms at hydrothermal vents have been estimated to live for more than 250 years. The ocean quahog clam, a species that lives on the continental shelves of the North Atlantic, was found in one case to be 507 years old, born before Christopher Columbus reached the Americas. These extraordinary lifespans reflect the energy economics of cold, deep environments, where metabolism must be slow to conserve scarce resources. Longevity becomes, in a sense, a byproduct of frugality. The seafloor contains the wreckage of ships spanning thousands of years of human navigation. Scattered across the ocean floor are the remains of ships, from ancient wooden trading vessels to modern steel-hulled cargo ships and warships, representing thousands of years of human activity on the sea. The deep ocean preserves these wrecks extraordinarily well. In the cold, dark, low-oxygen conditions of the deep seafloor, organic materials that would decay in weeks at the surface can persist for centuries. The Titanic, which sank in 1912 at a depth of about 3,800 meters, has been extensively documented by remotely operated vehicles and shows both remarkable preservation of some materials and significant ongoing deterioration of others. Ancient amphora-laden trading vessels from the Mediterranean are preserved in sufficient detail to reveal the routes, goods, and sometimes even the personal belongings of merchants who lived more than 2,000 years ago. The deep seafloor is also, in a sense, an archive of human maritime history. Bristlemouth fish are likely the most numerous vertebrates on Earth. In the mesopelagic zone, the twilight layer between 200 and 1,000 meters, lives a group of tiny fish called bristlemouths or cyclothones. These small, dark fish, rarely more than a few centimeters long, are thought to be the most numerous vertebrate animals on Earth, with populations estimated in the quadrillions. They are so abundant that they form dense layers detectable by sonar, contributing to the deep scattering layer, a zone of high acoustic backscatter that puzzled sonar operators during World War II, appearing as a false bottom that moved up toward the surface at night and sank again at dawn, following the daily vertical migration of the organisms within it. Despite their extraordinary abundance, bristlemouth fish are poorly known. They are difficult to collect intact, they deteriorate rapidly, and the depths at which they live are rarely studied in real time. The seafloor of the Mediterranean Sea preserves evidence of when the sea nearly dried up. Between about 5.9 and 5.3 million years ago, the Mediterranean Sea was largely cut off from the Atlantic Ocean by tectonic uplift at the Strait of Gibraltar. Without the Atlantic's input, the Mediterranean gradually evaporated over hundreds of thousands of years into a vast, extremely deep basin dotted with salt lakes. The most extreme example of evaporative drawdown of a major ocean basin known in geological history. This event, called the Messinian Salinity Crisis, left behind enormous deposits of salt and gypsum that are preserved beneath the current floor of the Mediterranean. When the Atlantic eventually broke through the Gibraltar Barrier again, the resulting flood of water was among the most dramatic events in the recent geological record, an enormous cascade of seawater refilling the basin over a period of months to thousands of years, depending on the model. The evidence for this event is preserved in the sediments and rock layers beneath the current seafloor. Underwater robots have transformed deep-sea exploration. Until the development of remotely operated vehicles and autonomous underwater vehicles in the latter half of the 20th century, direct observation of the deep seafloor required the use of crude submersibles, expensive, limited in duration, and capable of carrying only 2 or 3 people. Modern ROVs, connected to a surface ship by a fiber-optic tether, can remain on the seafloor for days, transmitting high-definition video and allowing scientists on the surface to manipulate the environment and collect samples through robotic arms. Autonomous underwater vehicles, or AUVs, can be programmed to conduct surveys of large areas without any connection to the surface, navigating by acoustic positioning and acoustic Doppler current profiling. These tools have accelerated deep-sea exploration enormously, opening areas of the seafloor to study that would previously have required years of expensive crude operations. The seafloor as we know it today is largely a product of what ROVs and AUVs have revealed. Some deep-sea fish produce sounds that carry across long distances. The deep ocean is often imagined as silent, but it is not. Beyond the bioluminescent light shows and the chemical communication of many deep-sea organisms, sound plays an important role in the biology of the deep. Certain fish produce sounds for communication and mate attraction. The drumming of the plain-finned midshipman fish, which inhabits the seafloor along the Pacific coast of North America, is loud enough to penetrate the hulls of houseboats and has been mistaken for machinery noise by people on the surface. Deeper-dwelling species also use sound, though their vocalizations are less studied. The deep ocean itself transmits sound extraordinarily efficiently, particularly in the SOFAR channel, where low-frequency sounds can travel for thousands of kilometers. The soundscape of the deep ocean, made up of animal vocalizations, geological events, shipping noise, and the distant signatures of storms, is an active area of ecological monitoring. The color black is a common adaptation among deep-sea animals for reasons of survival. In the complete darkness of the deep ocean below about 1,000 meters, where the only light is the bioluminescence of living organisms, an animal that absorbs rather than reflects that light has a significant advantage. A bioluminescent flash in the dark is visible to a predator from a significant distance. A black surface absorbs virtually all incident light, reflecting almost nothing, making the animal nearly invisible in an environment where even a faint reflection can mean death. The blackest known biological material comes from deep-sea fish, specifically from the skin of certain species that absorbs more than 99.5% of incident light, more effectively than many engineered black materials. This extraordinary darkness is produced by a specific arrangement of melanin-containing granules in the skin cells, which trap and absorb photons rather than reflecting them. It is one of the most extreme examples of camouflage adaptation anywhere in the animal kingdom. The deep ocean has been shaped by asteroid impacts as well as geological processes. The geological record of the ocean floor includes evidence of catastrophic events that came not from within the Earth, but from space. The impact of the asteroid or comet that ended the age of dinosaurs, approximately 66 million years ago, left a distinctive chemical signature in deep-sea sediments worldwide. A thin layer enriched in iridium, an element rare in the Earth's crust but common in meteorites, deposited globally as the impact's debris settled from the atmosphere. This layer, the Cretaceous-Paleogene boundary, is one of the most recognizable features in the sediment record of the world's oceans, and its consistent presence across geographically separated sediment cores was an important piece of evidence in establishing the impact theory of the mass extinction event. The deep ocean floor is not only a record of Earth's own geological history, it is a record of events that arrived from beyond the planet. Submarine groundwater discharge carries fresh water from land into the ocean through the seafloor. Along many coastlines, fresh water does not only reach the ocean by flowing across the surface in rivers and streams. It also seeps through the sediment and rock of the continental shelf, emerging through the seafloor in a process called submarine groundwater discharge. This hidden pathway can carry significant quantities of freshwater and dissolved nutrients into coastal and nearshore areas, sometimes supporting local biological productivity and influencing the chemistry of coastal waters. In some areas, submarine groundwater discharge is comparable to or even exceeds river input as a pathway for delivering nutrients to the sea. It is poorly measured and poorly understood, partly because it occurs invisibly beneath the water surface and partly because it varies significantly in space and time. Recognizing its importance has changed how scientists budget the water and nutrient fluxes between land and ocean. The deep sea has its own form of weather, driven by density differences in the water. The dynamics of the deep ocean are not static. Temperature changes at the surface, variations in salinity driven by evaporation and rainfall, and the sinking of dense water at high latitudes create flows in the deep ocean that, while slower than surface currents, are persistent and influential. In some areas, these deep flows are channeled by topographic features, ridges, seamounts, fracture zones, into jets and eddies that can be surprisingly energetic. Bottom boundary currents, flowing along the base of continental slopes, can carry sediment for hundreds of kilometers. Internal waves, generated where deep currents interact with underwater topography, can propagate enormous distances through the interior of the ocean, breaking eventually on distant slopes and mixing the water column in ways that influence the distribution of heat, nutrients, and organisms. The deep ocean is not still. It moves according to its own rhythms, on its own timescales, by its own rules. Shipworm damage to wooden ships helped motivate the development of iron-hulled vessels. The deep destruction of wooden ships is not only a consequence of the physical processes of the seafloor. In shallow and coastal waters, a group of bivalve mollusks known as shipworms have caused immeasurable damage to wooden structures throughout maritime history. These animals bore into submerged wood, using it both as habitat and as a food source, tunneling through the interior while leaving the surface largely intact, a pattern of damage that could be invisible until a ship's hull was catastrophically weakened. Ancient fleets and harbor structures were regularly lost to shipworm damage. In deeper water, below certain depths, wood-boring organisms become rarer, and organic material sinks relatively intact to the seafloor. The finding of ancient wooden shipwrecks on the deep seafloor in remarkable states of preservation reflects, in part, the absence of the organisms that consume wood in shallower waters. Oceanographers use Argo floats to monitor the deep ocean continuously. Since the early 2000s, an international program called Argo has deployed thousands of autonomous profiling floats across all the world's oceans. Each float drifts at a depth of about 1,000 meters, sinking to 2,000 meters every 10 days to make a measurement profile of temperature and salinity as it rises back to the surface, transmitting its data to satellites before sinking again. The Argo network provides real-time data on ocean temperature and salinity at depth on a global scale for the first time in the history of oceanography. It has transformed our understanding of how the deep ocean changes over time, how heat is stored and redistributed by the deep circulation, and how the ocean is responding to climate change. Before Argo, the interior of the ocean was sampled sparsely at irregular intervals by occasional ship expeditions. Now it is monitored continuously by a fleet of thousands of robotic instruments drifting through the darkness. The remains of ancient river deltas are preserved on the continental shelves. During the last ice age, when global sea levels were roughly 120 meters lower than today, the continental shelves of the world were largely exposed as dry land. Rivers extended across these broad plains, building deltas and meandering across terrain now submerged beneath tens of meters of seawater. The remnants of these ancient landscapes, buried valleys, submerged dune fields, the hardened mud of ancient lake beds, are preserved beneath the thin veneer of sediment that has accumulated since the seas rose again at the end of the Ice Age, about 12,000 years ago. High-resolution sonar surveys of the continental shelves have revealed these features in striking detail. In some areas, the traces of ancient human habitation, stone tools, hearths, the bones of now extinct animals, have been found in sediments on what is now the seafloor. These submerged landscapes represent vast areas of human prehistory that were inundated by rising seas and have yet to be systematically explored. The sound of the ocean floor can reveal its geological structure. Geophysicists studying the structure of the seafloor and the crust beneath it use sound in ways that go far beyond simple echo-sounding depth measurement. Seismic reflection profiling, in which pulses of acoustic energy are directed into the seafloor and the reflections from different layers are recorded, produces cross-sectional images of the sedimentary and crustal structure to depths of many kilometers. Seismic refraction techniques, using receivers placed at distances from the sound source, probe still deeper into the crust and upper mantle. Together, these methods have revealed the layered structure of the oceanic crust. The thin upper layer of basaltic pillow lavas, the thicker layer of sheeted dikes below, and the deepest layer of gabbro, as well as the sediment thickness, the depth of the Mohorovičić discontinuity between crust and mantle, and the location of magma chambers below active spreading centers. The internal architecture of the seafloor, invisible to any direct observation, has been mapped by listening to echoes. Life exists even in the most chemically hostile deep-sea environments. Among the most extreme examples of life's adaptability in the deep ocean are the communities found in brine pools, depressions in the seafloor that are filled with water so salty it is several times denser than normal seawater, unable to mix with the water above and lying at the bottom of its basin like an underwater lake. The boundary between normal seawater and the brine, called the halocline, is a sharply defined interface that can look, from a submersible, like the surface of a still pond. In most brine pools, life is sparse or absent within the pool itself because the salt concentration is toxic to most organisms. But around the edges of the halocline, where normal seawater meets the chemically rich brine, there are often thriving communities of bacteria and mussels that have evolved to exploit the nutrients, particularly methane and hydrogen sulfide, that diffuse outward from the brine. Even here, at the edge of chemical tolerance, life finds its way. The seafloor records the history of Earth's atmospheric oxygen. The deep-sea sediment record contains evidence not only of climate change, but of changes in the fundamental chemistry of Earth's atmosphere over geological time. In sediments older than about 2.4 billion years, iron-bearing minerals appear in forms that indicate the ocean and atmosphere were nearly devoid of free oxygen. Then, in a transition called the Great Oxidation Event, the chemistry of seafloor sediments changes dramatically, reflecting the growing presence of oxygen produced by cyanobacteria. More recent sediments record subsequent changes in ocean oxygenation, including episodes of oceanic anoxia, during which large areas of the deep ocean became depleted of oxygen, sometimes with catastrophic consequences for marine life. The chemistry of iron in deep-sea sediments has proven to be one of the most sensitive recorders of the history of oxygen in Earth's environment, a record that extends back billions of years. The deep ocean floor contains surprising quantities of glass. When lava erupts underwater, whether at the mid-ocean ridge, at submarine volcanoes, or at the margins of lava flows from island volcanoes, it cools so rapidly on contact with cold seawater that it does not have time to crystallize. Instead, it freezes into volcanic glass, producing the characteristic rounded pillows of pillow lava that cover enormous areas of the ocean floor. These glassy rinds, which can be only a millimeter or two thick on each pillow, preserve the chemical composition of the lava at the moment it erupted, before any mineral crystallization could alter it. By analyzing deep-sea volcanic glass, geochemists can read the composition of the mantle from which it derived, tracing changes in mantle chemistry across different parts of the ocean floor and over geological time. The ocean floor is, among many other things, a vast collection of precisely dated, chemically preserved samples of Earth's interior. Seafloor hydrothermal systems influence the chemistry of the entire ocean. The circulation of seawater through hydrothermal systems at the mid-ocean ridge is not simply a curiosity of the deep-sea environment. It is a globally significant process that modifies the chemistry of the ocean on a planetary scale. It has been estimated that the entire volume of the world's ocean cycles through the hydrothermal systems of the mid-ocean ridges once every 8 to 10 million years, a period short enough, on geological timescales, for the cumulative chemical exchange between seawater and hot basalt to substantially alter the composition of both. Magnesium is removed from seawater and calcium is added. Sulfate is reduced to sulfide. Trace metals are selectively concentrated or diluted. The pH and alkalinity of the deep ocean, which in turn influence the ocean's capacity to store carbon dioxide, are partly governed by the rate and extent of hydrothermal circulation. The heat and chemistry of the mid-ocean ridge reach, indirectly, into every corner of the ocean. The continental margins are among the most geologically active regions on Earth. The boundaries between continental and oceanic crust are not gentle transitions. Along active continental margins, those at the edge of a subducting oceanic plate, the seafloor is the site of some of the most intense geological activity on the planet. Frequent earthquakes, active volcanism, rapid sediment accumulation, and significant deformation of the crust. Along passive continental margins, those where continental crust simply transitions to oceanic crust without an active plate boundary, the geology is quieter, but the sediment record is often extraordinarily thick and detailed, preserving hundreds of millions of years of depositional history. The continental margins are where human civilization has most directly interacted with the deep ocean. The fishing grounds, the oil and gas fields, the undersea communication cables, the port cities built on the accumulated sediment of ancient river deltas. They are the deep ocean's interface with the human world, and they remain among the most geologically complex and consequential regions on Earth. The deep seafloor has its own form of ecological succession after disturbance. When the seafloor is disturbed by a volcanic eruption, a landslide, the arrival of a whale carcass, or the disturbance caused by human activity, the recovery of the biological community follows a predictable sequence of stages that ecologists call succession. Pioneer species are the first to colonize bare or disturbed sediment. Bacteria, small worms, and mobile scavengers arrive quickly, exploiting the new conditions. Over time, as organic matter accumulates and the physical environment stabilizes, a more diverse community develops, including sessile animals like corals, sponges, and tube worms that build structure and create habitat for other organisms. The timescale of this succession in the deep ocean is vastly slower than on land or in shallow water, where a disturbed area of temperate forest might recover its original diversity in decades. A comparable area of abyssal plain might require centuries to millennia to return to its pre-disturbance state. This slow recovery is central to concerns about human activities that disturb the deep seafloor. Isotopic analysis of deep-sea sediments has revealed the history of ice ages. Among the most powerful tools in paleoclimate science is the analysis of oxygen isotopes in the shells of foraminifera preserved in deep-sea sediments. Oxygen occurs in nature primarily in two stable forms. Oxygen-16, the lighter and more common isotope, and oxygen-18, the heavier and rarer one. During ice ages, water molecules containing the lighter oxygen-16 evaporate preferentially from the ocean and become locked up in continental ice sheets, leaving the remaining ocean water slightly enriched in the heavier oxygen-18. Foraminifera that build their shells from this water record this isotopic signature. By measuring the ratio of oxygen isotopes in foram shells at different depths in a sediment core, scientists can reconstruct the history of global ice volume, and therefore global temperature, across millions of years. The result is a detailed record of the ice age cycles that have dominated Earth's climate for the past several million years, driven by subtle changes in Earth's orbit and the tilting of its axis, preserved in the chemical composition of microscopic shells on the ocean floor. Cold water upwelling along continental margins brings nutrients to the surface and supports rich fisheries. Along certain coasts, the western edges of continents in particular, including the coasts of California, Peru, Namibia, and Morocco, persistent winds drive surface water away from the coast. This surface water is replaced by cold, nutrient-rich water drawn up from depths of 100 to 300 meters. This process, called coastal upwelling, brings vast quantities of nitrogen and phosphorus from the depths into the sunlit surface layer, fueling explosive growth of phytoplankton and cascading up the food web, supporting some of the world's most productive fisheries. The Humboldt Current system off the coast of Peru and Chile is the most productive fishing zone per unit area in the world, its productivity driven by cold, nutrient-rich water drawn up from the continental shelf and sloped by persistent southerly winds. The richness of these fisheries is entirely a product of what happens on and near the seafloor beneath the upwelling zones. Deep-sea expeditions have recovered materials with no equivalent elsewhere on Earth. The extreme conditions of the deep ocean, the cold, the pressure, the darkness, the chemical environment, produce materials and organisms that are genuinely unlike anything accessible at the surface. The protein structures of deep-sea organisms, tuned by millions of years of evolution to function at high pressure, are of significant interest to biochemistry and biotechnology. Hydrothermal vent minerals include compounds that form only under the specific combination of high temperature, high pressure, and extreme chemistry found at the vents. The sediment itself contains a record of past ocean conditions, biological productivity, and climate variability that is accessible nowhere else. Research expeditions to the deep ocean consistently return with samples that challenge existing knowledge, organisms, minerals, and chemical signatures that do not fit neatly into the categories established from surface science. The deep ocean is not a remote and irrelevant environment. It is one of the richest repositories of scientific information on Earth. And so, we rise slowly now. Back up through the darkness, through the pressing weight of water, through the twilight zone where the first traces of blue reappear, through the gradual brightening as the surface draws near. Back from the vent fields and the sediment plains, from the whale falls and the silent trenches, from the ancient basalt and the patient microbes, from the slow and enormous world that lies beneath everything. The ocean floor is not a remote place, not truly. It lies beneath every ship that has ever crossed an ocean, beneath every storm that has ever gathered over the water, beneath the fish that fed civilizations and the currents that have shaped climates for millions of years. It is the hidden foundation of the world, vast, ancient, and still largely unknown, shaped by forces that have been working without pause since the Earth first formed, and that will continue working long after the last human thought has been thought. You have drifted tonight through a place that most people never visit, even in imagination. You have felt the pressure of the deep and the warmth of the vents. You have passed through darkness lit only by living light. You have glimpsed the extraordinary patience of the deep, in the microbes that divide once in 1,000 years, in the corals that take centuries to build their towers, in the nodules that grow a millimeter per million years. That patience is still down there, right now, while you rest. Let your breath slow. Let the weight of the day dissolve like sediment settling in still water. There is nothing required of you in this moment except to release what you no longer need and let sleep carry you somewhere quiet. The deep ocean will continue its ancient work. The vents will keep burning. The currents will keep turning. The sediment will keep falling, one particle at a time, year after year, building its quiet record of everything that has ever passed through the water above. Consider subscribing to Some Neuromind. You're already the kind of person this channel was made for. But for now, let go of everything. Rest now. You've earned it. Good night.